Hello everybody. So now we will discuss the calculation of the diffusion coefficient for concentrated solutions. As we mentioned in the previous videos, the equations that we presented before were used to calculate the diffusion coefficient for infinitely diluted solutions, and we described what we mean by the infinitely diluted solution. So in case you have a concentrated solution, then you have to use another equation to get the diffusion coefficient, because it will have a different value. Of course, this is not a simple thing, and it requires a lot of experimentations and a lot of tests, but this is one of the simple recommended equations that we can use to calculate the diffusion coefficient in a concentrated solution. So exactly like what we did in the gas phase, when we wanted to calculate the diffusion coefficient in a mixture, we had to know the diffusion coefficient for each species and the mole fractions. So this is kind of similar. So here we need to get the diffusion coefficient of A and B in infinite dilution, and diffusion coefficient of B in A at infinite dilution, and we need to know the XB and XA, which are the mole fractions of A and B in the solution. So if we know these, then we can use this equation simply without any problems. It's going to be like a simple and straightforward substitution in the equation. So the last thing we will discuss in the liquid phase diffusion coefficient is the diffusion coefficient for electrically conducting liquids, which we call the electrolytes. So the diffusion coefficient can be calculated from this, and of course because of this equation, because we are discussing a solution that contains ions and it's conducting electricity, then this is going to be more of an electrochemical thing, and that's why the equation that we use to calculate the diffusion coefficient is kind of derived from the Nernst equation, which is an electrochemical famous electrochemical equation. And this equation states that the diffusion coefficient is a function of RT, and T is the temperature, of course. F is the Faraday constant. It's like a very well-known constant, and it's a function of the n plus n minus and lambda plus node and lambda minus node. N plus and N minus are the valencies of the cation and anion. So let's say I have the salt solution in water, which is calcium chloride solution, for instance. So it's CaCl2. When it is diluted in water or dissolved in water, it turns into Ca2 plus. So the calcium valency is 2, and chlorine valency is -1. So N for calcium is 2, and N for chlorine is 1. The last two parameters here, which are lambda plus node and lambda minus node, are the conductances at the infinite dilution or the limiting conductance. It means that as the concentration of the ions in the solution decrease, the electric conductivity will decrease. So these lambda plus and lambda minus node are the conductances at infinite dilution, when the concentration is very or at zero concentration, which is almost zero. Then this is going to be the limiting or zero concentration conductance. This is what we call lambda plus node and lambda minus node. So one is for the anion and one for the cation. So these are the parameters that we use to calculate the diffusion coefficient in conducting liquids. In the next video, we will discuss the diffusion coefficient in solid phases, and we will see 4 cases where we can calculate the diffusion coefficient in. So I'll see you then, inshallah. Goodbye.